Okay, this video is a little bit different because I've already done the solution and you can see it here on the screen. I'm going to go through the solution two different ways, one with up as positive and one with down as positive. Both are equally good ways to solve the problem. The problem, as you saw in your packet, is a ball is dropped off a cliff and is traveling 40 meters per second just before it hits the ground. How tall is the cliff and how long did it take for the ball to reach the ground? So first we identified that this is going to be using one-dimensional kinematics. That's from chapter 2. We have specified a coordinate system. That's right here. We're using up as the positive y direction. We're not going to need an x direction. What are we looking for? Well, we're looking for the height of the cliff, which is equal to the absolute value of the displacement, delta y. We expect, since it's an absolute value, we expect that to be positive. The height of the cliff should be a positive number, and the units are meters. It didn't say that we should put that, but I think it's a nice thing to put in there what units you're expecting. Time is going to be a positive number, and the units are going to be seconds. Here we have our motion diagram, and as you can see, it's traveling quite slowly here, and we'll designate that. And then right here, you can see it's moving quite fast. And that makes sense. It's speeding up as it goes. Starts off at 0 meters per second. We decided to call this position 0. And when it gets to the bottom, it's going 40 meters per second. It doesn't say in the problem, hey, it's going negative 40 meters per second. But what it does say is it's traveling 40 meters per second just before it hits the ground. We chose up as positive, so we need to make sure we make this a negative number. Otherwise, we're going to end up with some weird answers down here. Our acceleration is going to be negative. Again, the choice here of up is positive is what dictates the sign here. Acceleration due to gravity is always downward, but it's not always negative, as we'll see when we do number 9. One of the unknowns is the time. You notice that the acceleration and the time here are shown with this bracket. And so that's because it corresponds to the whole motion. Whereas this velocity and this position correspond just to that point there, and this velocity and this position correspond just to that point there. Okay, now we've done a good job visualizing the problems. We have our diagram. It's a motion diagram. We've identified what the knowns are, and we've even put them on the diagram next to where that part of the diagram is. So our initial states are here, our final conditions relate to that dot down there. We've put our unknowns over here and on the diagram itself. We did not need to restate the question here because it was a straightforward question. The only restating, I guess, was restating the answer, clarifying that this is going to be the height of our, the height of the cliff is going to be equal to the absolute value of the displacement. So we're saying, what is the displacement? And we can easily take the absolute value of that. There are 4 kinematic equations on your equation sheet for the y direction, and we picked these 2 equations because they each had just one unknown, and not only that, but those are the unknowns that we were wanting to find. And so, and honestly here I could have used the equation vy squared equals v naught y squared plus 2ay delta y. That would have been simpler if I had just solved for delta y as my unknown, since that's really what I was looking for. So I've got my plan, and then I execute the plan. The one thing I would keep in mind if you're entering this into your calculator is you need to enter parenthesis minus 40 parenthesis squared. If you just type in negative 40 and then square it and then divide by negative 19.6, you're going to get a positive number. And y should be a negative number here. If you're starting with this as 0, you should get a negative number for your y. And so just be careful entering in when you have a negative number and then a square be careful entering that into your calculator. The rest is pretty straightforward. We solved. The executing the plan really should be the easy part. Is the solution complete? Yes, we solved for both things we needed. We already talked about the signs, the correct units. Yes, we've got meters per second squared, so that's meters squared per second squared, divided by meters per second squared, so that does leave us with units of meters. And are the magnitudes of the answers reasonable? Oh, I forgot to do the units on this one, but this is meters per second squared divided by meters, I'm sorry, those units cancel, of course. But over here, we've got meters per second divided by meters per second squared, and so that's meter per second over meter per second squared, which, if we simplify, we just flip this over, and we do it twice, such that this whole thing here is equal to 1. Second squared over second squared over meters is 1, and then this part cancels, and then that cancels with one of those, and meters cancels, and that leaves us with seconds. So the units are correct, and the magnitude is reasonable. 4 seconds to fall roughly 250 feet. That sounds reasonable, and it's going 80 miles an hour roughly. So this all sounds pretty good. Let's look at the same problem again, but now using down as positive. There's nothing wrong with using down as positive. So most of the things are the same in here. I'll just point out this becomes a positive number. This is a positive number. The rest of this is the same up here. The plan is the same. Substituting the values in, well, we're substituting in different values. This becomes a positive number, positive. Now we end up with a positive answer for y. We started at 0, we went further into our positive direction, and so y is positive. But regardless, we were taking the absolute value. But it's still interesting to see how this y came out positive, and on the last page it came out negative. Here, both of the signs are reversed. We still get a positive value for time, as we should.